I'm really happy to announce our next guest speaker for the course, Professor Jiajun Wu. So Jiajun is an assistant professor here at Stanford in the Department of Computer Science, and he's a faculty member of the Stanford Vision Vision and Learning Lab. His research focuses on scene understanding with an emphasis on multimodal perception, robotics and embodied AI, visual generation and reasoning, and 3D understanding, which is the topic of today's lecture. And so I'll now turn it over to Jiajun to begin today's lecture.
Okay, yeah. So I'm Jiajun. I'm an assistant professor here, and I think a few years ago I used to teach this class, co-teach. So I heard this year is the 10th year anniversary, right? So you have guest speakers from different places. Okay, so today we're going to talk about 3D vision. So it might be kind of different from a lot of things you learned before, because I think in the past few weeks we talked about like convolutional neural networks and transformers and maybe vision language models and generative models as well for adjusting, right? Okay, yeah. So here for 3D, I think I'm going to first introduce a little bit on what are the 3D representations. So it's more like it's pretty distant from all the deep learning stuff. But then we're going to talk about how deep learning or AI has changed 3D vision and how they can be integrated in different ways, and we'll look into a few different applications about 3D generation, reconstruction, and stuff like that. Okay, so let's begin by looking into what are the possible ways to represent objects in 3D, because in 2D it's so straightforward. It looks like, okay, I just have pixels, right? I have a loading a file of a PNG file, a JPEG file. It's like 200 by 200 pixels. But how can we represent 3D objects? I think that's the first thing we want to look into. And 3D objects, they can be diverse. They can be at different scales. It can be like huge, large buildings and trees, complex structures. And if you zoom in, you can also see all the fine details. So what are the best 3D representations to represent all these different types of 3D objects at different scales with different features? And unlike images, where everyone just uses pixels, so we have 200 by 200, 500 by 500. The way to represent 3D objects, objects are also like you have geometry, you have textures, you have materials. But let's just maybe start by looking at geometry. And even just for 3D object geometry, there are so many different ways to represent them. We can basically categorize them into two different categories. One is called explicit representations. So where you can, in some sense, they're directly, I would say, explicitly representing part of the objects. This includes things like point clouds. If you have a cloud of 3D points, or a polygon mesh, or subdivisions, which we're going to talk about it, and others. And there's a different categories of object shape representations, which are often called implicit. So we're going to talk about them as well. So I'm going to expand them in a little bit detail later, including level sets, algebraic surfaces, distance functions. So they're basically representing 3D objects or their geometries as functions, which it is not directly, it's not as, in some sense, intuitive as, it's just a collection of points. But as we'll see later, they also have their own advantages and weaknesses using implicit representations. So every choice, they have their, suitable task and type of geometry. In particular, in the context of deep learning, they may also have their own strengths and weakness when you want to apply a deep learning method on top of it. So when do we choose representation? We have to store them. So pixels are easy to store because it's just a matrix. But then 3D point clouds are kind of more irregular. And also, especially if you use some implicit representations, like representing object as a function, how would you store that in a computer? And how does it support, creating of new shapes? And especially now, let's say maybe the input is a picture or the input is a language descriptions. And different type of operations. You have a 3D objects, and then how can you edit it, simplify it, smooth it, filter it, and repair it? Right, so you can have to do a lot more. For images, sometimes you want to do that too. You want to edit it. You want to edit it using language. You want to edit it using stroke. And how can you edit or perform any type of operations on 3D objects? And rendering, how can you turn that 3D objects render into into 2D pixels? In some sense, the 3D vision is to invert the process, right? How can you go from 2D images to reconstruct the 3D objects? So how does it support all these different things, including end-to-end animations, especially if you are modeling, let's say, 3D humans or animals, and you want to animate them. So all these factors need to be considered. And something else, of course, it sort of connects to all these is also their integration with different deep learning methods for, let's say, shape editing, rendering, inverse rendering, and animation as well. So very quickly, we can go through some of these representations like point clouds. So point cloud is probably the simplest representations. It only has 3D points. It doesn't have connectivity, so it doesn't capture how these points are connected. So you basically just have instead of having an n by n matrix, which is about the pixel values of all the pixels in a picture, now you have a 3 by n matrix where 3 is XYZ coordinates of these individual points, and you have a number of points. So sometimes you can represent the surface normals of the point as well, so that you have not only where the point is in the 3D space, but also to which direction it's facing. So you have the surface normals, which give you a bit more information, and sometimes people call them surfals, which is points with orientations. And yeah, so why do you need surface normals? Because if you want to render them, you want to say how the object look like. Then that means you have to often specify a lighting source, right? Where's the lighting coming from? But to make the rendering look realistic, you have to consider how the lighting, coming from a certain direction is going to interact with the point. And this is where the surface normals is used to help you to make the rendering look realistic, like you can see here. So how can you get points? A benefit of the point cloud, it is often a raw format that you will get from a lot of the 3D sensors, including these kind of depth sensors, including some 3D scanners. And, nowadays, I think if you can even use an iPhone, I think they have an AR kit or these kind of software allow you to scan 3D objects, but the raw output of those sensors, they're still kind of 3D point clouds. Now, of course, after that, you have to process them and fuse them to make it like maybe objects with textures. They often results from scanners. They can potentially be very noisy, and there are things like this, and then you want to fuse them, merge them, repair them. And in this part, you have to consider how these different pictures can be registered, to give you the shared point cloud. And, they're very flexible. So because you can move points here and there, so you can use them to represent basically any type of object geometry. You're not constrained by the topology or stuff like that. It's kind of useful for large data sets because sometimes you have to consider a very diverse set of objects. But because points are already in some sense you consider to have being pre-sampled, right? So, if you have a lot of points, if you're representing objects but your points are sampled in an uneven way, in the sense that you have a lot of points, let's say on the head of the rabbit, but you have very, very few points on the tail of the rabbit, then it will be actually hard to draw samples from these undersampled regions. So sometimes when people consider, sampling points, you have to design algorithm to make sure you sample them roughly evenly, across different parts of the objects. And other limitations are, it's not obvious how we can directly perform sometimes the very useful operations like simplification or subdivisions on these objects. It doesn't directly allow you to do smooth rendering. There's no topological information, right? So for example, here, if I give you a collection of points, then you can't even tell, if this is like a torus or this is like these kind of ring-like shapes, right? Because it doesn't tell you how these points are connected. So it's kind of a partial information about what the object is if you just have the point clouds. So naturally, people will say, okay, how can I actually capture more information so that I can distinguish between these two different objects? Then naturally, that goes to the polygonal meshes, right? So it represent the objects as still as a collection of points, but then also how these points are connected. So now you have not only the points, but also the faces, the surfaces. And this is arguably I would say the most widely used representations for 3D objects in all these graphics engines and in computer games and stuff like that. Basically it is all represented as polygon meshes. But you can see that, to represent faces, it is more complex because often you have to consider, especially if you're looking at raw meshes, then every face may have a different number of points. It may have 3 points, it may have 4 points, it may have 5 points, and how you can represent them, especially given their irregularity, how you can integrate them with neural networks, especially in the early stage when people start with convolutional neural networks. Okay, they always assume a fixed resolution. But here you have, not, obviously a variable, dimension of, these raw information. How does that integrate with deep learning? That has been some big challenge. That's why, deep learning with 3D vision kind of started kind of late because people are thinking about how we can adapt all these deep learning methods to deal with all these, complex representations for objects which are not as unified as, images. But meshes are really widely used, and they can be, very complex meshes that capture all the details. For example, you have scanners, you get points, and then you fuse them, and you apply some algorithm. You can get, very large mesh. This one has 56 million triangles and 28 million vertices to represent a sculpture. And you can have even larger ones. Let's say from Google Earth, they have trillions of triangles try to represent basically all the buildings on Earth. The nice thing about meshes, it supports a lot of operations like subdivisions. Oh, I want to have more details, and how can I use more meshes to capture more details of the shape? And you can do simplification as well. Sometimes you want to process things very fast. So I don't need that many meshes. I just want to simplify it. And so there are existing algorithms that allows you to do that as well. And regularization. If you get an irregular mesh, and sometimes you want to regularize them so that every face is a triangle. They always connect three vertices. They have roughly the same size, and so that it's easier for processing, and they have more, obviously, good properties that supports future processing of different graphics algorithms. And meshes, there have been people who develop these algorithms as well, so that you can ensure that, basically points at different regions, they're roughly evenly sampled, so that it won't be the case that, okay, let's say the head of the tail, or the head of the rabbit is much more densely sampled than the tail, and these kind of things. Okay, so this is kind of one type of shape representations, and there are other type of shape representations, for example, parametric representations, because objects are not just totally irregular. It's not just often a collection of points and meshes. They're very general, but sometimes you lose a lot of information. If you look at, let's say, your chairs or the tables, you have all these kind of straight lines, right? So how can you represent these kind of straight lines? And when people design them, they often use some of these parametric representations. So you can represent shapes as a function, right? So think about it, so when I design them, I can, it's really, if I want to represent a surface or represent a curve, right, the underlying degree of freedom is actually lower. Often, if I have a curve, there's only one underlying degree of freedom. That's why I can represent a curve using a function f of x, right? I just vary x and get a value of y. So you can use basically all these different types of functions in 2D, but also more often in 3D, right, to map a certain number of variables, the underlying intrinsic dimensionality of the objects, which are often, let's say, in 2 or even 1, and then map it into the 3D space. And then this allows you to represent a 3D objects in the parametric representations using basically a set of functions, right? You can do that for curves. Let's say in circles, right? Basically, if you want to represent a circle, you don't really need one way is you sample a number of points, right? Or you can even connect them, like a meshes, you're using the lines. Another way is you just represent the curve, the circle as this function, right? Basically, there's a sine function and a cosine function, and you just vary one variable, which is t. You can think about it as the degrees or the angles, and it will map it to all the points on the circles, right? So here now you can use a function to represent a parametric representations for curves in 2D, and of course you can do that in 3D as well. If you want to represent a sphere, all you need is just like 2 degrees of freedoms, U and V, and then you can go through these functions so that you can map them to every point in the 3D space for this sphere, right? So people have designed, I'm not going to detail here, but more complex parametric representations like Bezier curves and Bezier surfaces, which allows you to represent these kind of pretty flexible and smooth surfaces in 3D using basically a few control points. So you basically use these Bezier functions to capture the underlying lower dimensionalities of these surfaces, and then you can map the underlying low dimensionality into these kind of flexible shapes. And they also allow you to do things like subdivision, so you can, trying to get more details into the surfaces and to make it more fine-grained and stuff like that. Okay, so that would be the second category of shape representations. You can represent 3D objects in a non-parametric way, like a collection of unordered points, or their connections as meshes, or you can represent them in a parametric way, where you have a function, basically, and by varying a few parameters that are underlying the true degree of freedoms of the object geometry, you can map them into more complex shapes. So basically everything here, as I said, it has been, if you remember at the very beginning, we said there are 2 types of ways to represent object geometry. One is explicit, there's more implicit. And all of them, they fall into this category of being quite explicit, right? So it's like I have points, and points are just directly points on objects. And for the surfaces or for parametric curves as well, they directly map it, right, to the points on the objects. So their explicit representations, they have a lot of benefits. First, they have you map all the points directly, so you can get all these points. In general, you can And every point I have, let's say I have a Bezier surface representations. I can basically sample 2 points and UV in this underlying lower dimensional space, and then going through that function, I map it to a point in the 3D space, right? So I directly get a point on the 3D in the 3D space. So all points are given, in some sense, you can say directly. I can directly get all the points. So it's very easy for us to sample points, right? So let's say I have this torus, and I have represented it using this f function. So now my question is, can you just sample some points on the surface of the object for me? This is so easy because I will just, randomly put in some u and v values. I just randomly sample those u and v values and then let them go through this function. And it will just, compute and give me some of the 3D points which are guaranteed to be on the surface of the object, right? So sampling is much easier. So what is hard about these explicit representations? The hard thing is, it's very hard in some sense, to test whether a point is inside or outside the objects. Similarly, if I represent a sphere as this function, and it's easy for me to sample points on the sphere, but it is hard for me to say, now I have a different, I have a query, right? I say this point 3/4, 1/2, 1/4. I have this point in the 3D space. Is it inside object or is it outside object? Right. I think we can maybe, actually, I'm not even sure about that. So it is actually kind of hard to test, whether a certain point is inside or outside object. So you can see that explicit representations it's all these representations, they have their own strengths and weaknesses. And for explicit representations, it's actually pretty easy to sample points, which are very useful because sometimes you want to convert them into, let's say, a collection of points, and then you want to apply whatever your point neural networks on it. But it's hard to test if a certain point is inside or outside object, which may have some issues. For example, let's say if you want to use a neural rendering methods, and nowadays a lot of these neural rendering methods requires a lot of these kind of queries about whether a point is inside object or outside object, what will be the geometry or density of object at that particular point, what will be the material, or what will be the radiance or color of the object at that particular point, right? So explicit representations are not very supportive of, it's not easy to run these operations on these explicit representations. So naturally people thought, okay, maybe we can come up with a different type of ways to represent geometry. And here I say implicit representation of geometry, but as you can see later, a lot of these neural rendering methods or deep learning methods, they just extend these implicit representations for not only geometry, but also for colors and appearance of objects in 3D. So the idea of these implicit representations is now that I want to classify these points. So I assume, if the points are on the objects, they're on the surface of objects, then they satisfy some certain relationship. So for example, for a sphere, what will be the points on the sphere, on the unit sphere? The constraint they satisfy is, square of x and square of y and square of z, when you sum them up, they equal to 1, right? So this is the constraint they satisfy for all the points, on the sphere. All right. So more generally, you can write it down as, the constraint will be some function of x and y and z equals 0. Right. So in this case, the fx and y, the function will be x squared plus y squared plus z squared minus 1, right? So that would be the function here. But more generally, you can think about it as, even for complex shapes, you can represent, and sometimes, these functions can be so complex that you don't even have a closed form. So how can I represent an f? I don't know. I just write it as a neural network. My hope is a neural network will be able to represent it. But in general, the idea is, you have some function, or some constraints that the points on a certain object will satisfy. And this is the way you will represent an object, and this is called implicit representations, which started with geometry, but as I said, now use it in all these different ways, representing textures, materials, appearance, and all these things. So the good thing about implicit representation, let's start with the bad thing. The bad thing about implicit representation is now it's actually much harder to sample points, right? I tell you, okay, this is the constraint. Let's say this torus satisfy, right? Okay, every x and y and z, if I put into this function and the output is 0, then yeah, they must be on the surface of this object. But then how can I get a couple of these x, y, z, tuples? That would be very hard because they're required to solve this function. And this function is maybe not too hard to solve. Maybe you can still solve that using some high school math. But when the function gets really complex, for arbitrary shapes, it becomes much harder to solve these functions. So it's not easy to actually now sample points on the surface of the objects if you are representing the objects implicitly. But benefit, the strength of that is now it's actually pretty easy to test whether a point is inside the object, outside the object. Because, if I want to do testing, I just have a query. Then this is so easy because it's inside or outside. I just send it into that function. I'll get a value, or the value is, okay, minus 1/8. Okay, this is smaller than 0. So, because I assume, the object is represented by this function, and all the surface point on the object, they satisfy that function equals 0. Anything that's, I would say lower than 0, it's negative. If the output value is negative, then the point must be inside the object. And if the output value is positive, then the point must be outside the object. Right. So now it becomes much easier to test whether a certain point is inside or outside object, although it becomes much harder to sample a number of points on the surface of object. So you can see now there's a clear trade-off between these implicit and explicit representations. Here we talk about geometry, but this distinction and the contrast between explicit and implicit representations I think is very important and fundamental. It is behind development of deep neural networks when they apply to 3D data in general, as we'll see later. Okay, so before it's been 25 minutes, so I promise I spend no more than 5 minutes, and then we're going to talk about deep learning. So before we talk about how deep learning can be applied to 3D representations in general, a little bit more on implicit representations is some other features of implicit representations. The good things about them is it's easy to compose them, right? So sometimes you feel like, oh, if I have to represent everything with a function, that seems great, if I have a closed form, but also seem very constrained because every closed form I can write it out. The geometries look very, very regular. So if I want to represent the shape of a cow, how would I represent that? What would be the function I can write for the shape of a cow? It's just not obvious. But the nice thing about implicit representation is you don't have to write everything in one shot because it's so easy to compose them, right? You can actually perform logical operations on these implicit functions. Let's say you have two objects and you find the unions or intersections or differences. You can, again, they're just values, right? So you put XYZ onto this function, you get a value. You put XYZ onto that function, you get a value. You can just do, arithmetic operations on top of these values, and that allows you to compute the unions or intersections or differences between these objects. And eventually you can compose them to develop pretty complex shapes. And this is actually, behind support a lot of these industrial designs when people are designing, complex parts for, I would say, when you're doing manufacturing you have to fabricate some complex shapes. A lot of these designs are done by these kind of CAD models, computer-aided designs, and they're composing these implicit functions using simple logical operations. And, you can also do things that beyond just logical. You can even add things up, especially if you have a distance function where every point is sort of like, the positive value and the negative value, the values actually have meanings because they indicate how far you are to the surface of the object. So you can even add them up, and this allows you to smoothly blend the shapes, right? So you can see that here, if I have a distance function, and here I just want to represent a vertical line. Okay, this is here, and then anything that's -0 is to the left of the line. Anything that is positive is to the right of the line. And then you have another line represented using a different function. So what happens if you add them up? If you add them up, then it naturally becomes an interpolation between these two shapes. Right? This is an example of doing things in 1D. But you can imagine, you can even similar doing things in 3D in the sense that, okay, now you can actually even blend these different shapes. And these distance functions can be arbitrarily composed and allow you to create actually pretty complex worlds like this. And this is not easy, but you can even think about, you can construct really complex with all the details worlds by just by difficulty, but compose these different functions. But they are actually very expressive if you're very good at it. Okay, so we said, okay, we have parametric representations that can be explicit, that directly give you points on the 3D surface, or we can have parametric representations like these functions, but they're implicit, right? So they're just like, okay, now you can only try to verify if the point is inside and outside an object, but then you can also compose them to build more complex shapes. And is that possible for us to also have implicit representations that are non-parametric, like point style, but then you also querying functions? Or sometimes they actually do have things like that. This eventually goes to methods like level set methods, right? So implicit surfaces are very nice because, as we said, it's easy to merge them, it's easy to split them, but sometimes, it's hard to describe, as we said, complex shapes in closed forms, right? You have a cow, how would you represent it? Okay, you can compose them, but if every time I have to query whether a certain point is inside a cow, you have to have hundreds of functions and you perform all these add and or, and, or, plus, minus operations, then it takes a long time. So what if I just pre-query, right? So I have a 3D space and I just sample, let's say, 100 by 100 by 100 grid, right? So, and then I have now 1 million points pre-sampled. And for these 1 million points, I just pre-compute whether they're inside the objects or outside the objects, what is the distance of these 1 million points to the surfaces for complex shapes. So you can pre-compute them, and then you can store all the values in the matrix. This is in 2D, but you can, this is for visualization, but in practice this is in 3D, right? So you have a 3D matrix that store all these pre-computed values of the distance functions. So now you're sort of, in some sense, you still have implicit representations, but because you have pre-queried them, you turned it into a non-parametric representations. And even if you just look at this matrix, right, in 2D, you can now still find, okay, where the boundaries are. So where are the boundaries? They're just basically where, you have two adjacent values, one is positive and one is negative. Right. So that means there must be somewhere in between that the point here, they satisfy the function fx equals 0, which means the point must be on the surface. Right. So in that sense, you're sort of turning on parametric representations, which are implicit, into a non-parametric representations by pre-querying a lot of these points using the functions. And this allows you to have actually more explicit controls because you can now visualize them. You can say, I have this matrix and I can visualize them based on their values. And this is used a lot in things like, CTs and MRIs and all these like medical data. And a related thing is people may say, okay, what if I don't care about all these distance values? I can pre-query what's going on at all these points, but then I compute all the values, let's say +5, -5, but all I care about is whether this is inside object or outside object, right? So if it's positive, I'll just treat them as 1. If it's negative, which means they're inside object, treat them as 0, let's say. So if you binarize them, then this gives you a final representations, which is arguably the easiest to understand. This is called voxels. Right. So, you can pre-query where the implicit functions are, and then you have all these kind of, density sample grid. But now instead of storing, their distance functions, how far they are from the surface by going through the functions and give you +5, -5, you just binarize it. You only care about whether a certain point is inside objects or outside objects. Then you have a voxel representation, which is again like a 3D matrix. Can be 100 by 100 by 100, but for every point you have go through this function and query whether it's inside and outside objects. You have 1 or 0, and you can represent objects in a binarized way, right? So this gives you the final representation I'm going to talk about for objects in 3D. So I've introduced voxels in a kind of complex way, but from a different perspective, people may say, this is actually very easy to understand because in some sense, voxels actually have a lot of analogy as pixels because pixels are like 2D matrices. And now you have a 3D matrices, and voxels is basically just a 3D matrix, right? So, although you can see that they have connections with all the other ways that we can represent shapes. And the way I'm introducing it this way is, actually when deep learning come in, right? So first deep learning, when did it start, right? 2010, deep learning has been there for a long time. But the modern deep learning thing is 2010, Geoff Hinton started doing that on speech recognition. And then 2012, they have AlexNet, which is run on ImageNet. So you've learned all these, and they're all in 2D. Okay, now people say, okay, what if I want to do it in 3D, right? This is a very natural thought. So I want to go from 2D convolutional neural networks. 2012, there's no transformer, right? So how can I apply a 2D convolutional neural network on 3D data? And everyone knows we have all these different 3D representations. But which one to begin with, right? It turns out that people will say, okay, yeah, the people who started doing deep learning on 3D data, they're the computer vision people. They're not like the graphics people. They're like, okay, I've been working with pixels, and maybe the easiest thing I can do is just to, scale up. Instead of working on 2D matrices, I just make it work on 3D matrices. So that would be the simplest thing I can do. Instead of having a 2D convolutional neural network, I have a volumetric convolutional neural network. Then, which of these representations allow you or support a volumetric convolution? Right, it turned out to be this voxel representation. This is basically the easiest you can imagine. Right? So But the graphics people do not agree with that because the graphics people are like, oh, this voxel representation is really bad because it's very slow to compute as we talked about. We have to pre-sample all these values and there, you can look at the quality, right? It is so bad compared with meshes or point clouds. So people are like, why do you want to start with that? But the reason that people started doing deep learning on 3D data with voxels, because I think it's like, it's so easy to draw an analogy between pixels and voxels, and you just have to change one out of the code. That is, instead of doing 2D convolution, now do 3D convolution. Right, so that's sort of in some sense how things get started. Okay, but before I talk about the deep learning methods for 3D data, another aspect that's very important is the data, for 3D data, yeah. So beyond methods, data sets are also very important. ImageNet really prompted AlexNet and stuff like that. So for 3D, similarly, we have to collect a lot of data as well. So pre-3D, pre-deep learning, the common data set, the popular data set people often use is this thing called the Princeton Data Shape Benchmark, which has 1,800 models, 180 categories. So you can see they actually have quite a lot of categories, 180 categories. But there are only 1,800 models, which means there are like basically 10 models per category, which is so small. But back then it was considered pretty large, and people feel like, oh, this is already enough to do because we can't really make any of things really work well on them. And there was very little machine learning there. So prior to 2014, all these data sets are kind of more or less small. They may have a certain number of models, even up to 10,000, 9,000, 10,000. But, they're also divided into so many different classes. And so each class, you only have like 10 models-ish, or less than 100, I would say. So after that, people started by saying, okay, if we have ImageNet, can we also have the 3D data sets for shapes? So this is behind efforts of a few concurrent work, but really I think eventually they sort of consolidated into this thing called ShapeNet, which is, a lot of them are actually led by Stanford. There's Leo Gibas and Silvio Savarasi. So they led this kind of large data sets called ShapeNet, which has 3 million models. And so, but in practice, just like ImageNet, you have this large ImageNet and there's a smaller data set that people often use. So ShapeNet, similarly, you have a ShapeNet core data set, which is what people typically use. It has basically 50,000 models in 55 categories. Now you can see for every category you have 1,000 models on average. But in practice, it's not that balanced. So for chairs, you have actually a lot more. So that's why, people say, oh, now finally I have thousands of models on chairs. I can train some deep networks on it, right? Before you can have 10 models, you can't do anything. So that's how things started. And so there has been a few years where a lot of these advances and all the results are just presented on chairs and cards because these are like the largest categories in ShapeNet. And people feel like, okay, that's great, but then that's not enough. So we should move, even bigger. So in the past few years, this is work at AI2, the Allen Institute from Seattle, where what they did is they collected much larger data sets called Objectverse and Objectverse Extra Large, that you have roughly 1 million or 10 million models for different 3D assets. You can see they have much more categories. And they also have, these models on average also have higher quality, also with textures. So these are synthetic data sets, but also there are real data sets that are being produced, including, some of them are from like 3D scans. You just take 3D scanners. Back in 2016, people have been working on it. This is a data set called, I think, the Redwood data set or something. So you have like 10,000 scans of real world objects. And more recently, people have been building larger data sets where they also encourage people. I think this is an effort co-led by Meta and Oxford. So they encourage people to take data for them. They also pay people to take data for them. So people just using an iPhone, you have an object, you put it on the table, you use an iPhone, you take a 360 video around the objects, and then you get $1 or something like that. So they encourage people to take data for them. This is the first version. They have 19,000 videos of objects. These are like real objects, right? Because capturing real objects is much harder. And the Objectverse and all the things I talked about before, it was like synthetic objects. But these are like real objects. And then, also because a lot of the development in 3D vision algorithms, you can actually take these 360 videos and try to reconstruct, the 3D objects. So now you have paired data of the videos or images of objects as well as their 3D geometries and textures.